Very good morning, all of you, and welcome to the class. Last time we have started discussing about the hashing, and we have already discussed about the hash function being applied. And once hash function was applied, we have also talked of applying the corresponding situation of a collision. And if there are collision, then we have to resolve corresponding to synonyms. And the collision resolution techniques, we have all talked of two techniques. One was called as a chaining, and other technique was named as open addressing. So chaining is what we discussed last time, and today we are going to resume with the discussions of this. So there are some interesting concepts which we will learn today via this. They are very easy but very interesting, and some factual information how this was being done 40 years ago versus what is being done at the present scenario. So last time we have already seen that hash function becomes very critical to have good collisions resolution, or SUH, or simple uniform hashing, desirable. So good hash function is highly desirable for having minimum collisions. My aim has to be the collisions should be minimum. If I have to ensure that, so I have to choose hash function carefully. So how to choose hash function? There are two options. One is called as a divisor method, and other method is called as a multiplication method. Of course, there can be more methods also which can be designed, but these two methods are very frequently used, and we will understand quickly both of these. They are very easy, simple calculations, but yes, that makes a difference. For example, in both of these cases, the requirement is, we already know there are n key values or n records which are to be stored in general. Remember that, and we have m slots available in my storage table, which is effectively a kind of an array. And I want to store this. So array equivalent means m slots, effectively they have their indexes in the range of 0 to m minus 1. So I should be able to effectively generate hash function in a way that all hash functions should map keys or universe of keys to the range of 0 to m minus 1. That is going to be the index to be used. So one simplest method, which is called as a divisor method or division method, can simply be used as that if I have integer keys, or some way I'm able to convert my key into integer value, then I would like to apply a mode function. So bring your value to an integer value, and even if you have a string, do some calculations based on that which you convert that to key, and then you are able to take this. This automatically will give me the values in the range of 0 to m minus 1. So straight away it ensures that my m slots will be used, and of course there can be the collisions, and then we have to resolve it through chain. But if I say like this, then choice of m becomes very critical, because this will decide how many collisions will happen. For example, if I say that I'm having a college, say NIT Kurukshetra, and NIT Kurukshetra, let's say each year I have students which are students roll numbered as 1 to 200. So I could say, okay, my first year roll numbers are first year followed by 001 to 1200. Second year roll numbers, let's say start with the 2001 to 2200. Similarly, third year students, and similarly fourth year students. Now, knowing that I have effectively 800 students, maybe I will say, if I try to do roll number mode 900 or 800, let's say for safer side, I take mode of 900, or to be precise, let's say take of 1000. For some possibility, I take the mode function to be 1000. So effectively m chosen is 1000. Now, if I have chosen m like this, then what I can easily see is now that this is going to probably deteriorate my programming or my total possibility, or collisions are going to be very frequent, because effectively mode 1000 means last 3 digits. Effectively, I will have last 3 digits to be coming out. So from 1001 also, if I have, let's say, student roll number 1125 of first year, my mode will effectively give me something around 125. And if I have student with roll number 2125, that will also give 125. Similarly for 3125 also, and so and so. So collisions are going to happen. Although, if you see, probably the range of 201 to 999, these slots will be never getting a value. Now, so that means even if I have chosen M to be based on my total values, but in this situation, choice of M through this process led to a lot of collisions. Hence, choice of M becomes very crucial, especially when M in this case was effectively taken as a 10 raised to 3 if it was a decimal number system. Similarly, in a binary number system, if you choose M to be some power of 2, this is said to be a bad choice. It has been mathematically proven and otherwise also logically convincing that if you choose M to be this, effectively it will extract last P least significant bits. Least significant bits only will play the role, and other bits will have effectively been ignored. So it's not a good choice. So normally it is always advised that M should be a prime number, normally greater than or equal to the slots needed. So M should be chosen in a way, but that is a general thumb rule. So if we are not able to find a good prime number near, we are going to probably waste the space. So that also you have to think of, but this is the way it is decided. So it's one of the way, because now M's choice becomes important, and it is already, I have said, it is critical to decide. So the other alternate is also used, that is called as a multiplication method. So multiplication method is also another alternate to make a hashing. How does it work? It simply says that I will do, instead of making M to be very critical, choice of M will not make much problem. It will not be that critical, because I will not be fully dependent on M only. Using a prime number, the random distribution or simple harmonic, simple uniform hashing was better possible. And this random distribution could be achieved via prime number in a better manner. Mathematically, we know prime number will always not lead to prime vectors. So every time mode will generate some different values, and mathematically it is provable. But if I am not using that method, so it is a multiplication method, where ultimately I say, yes, my index generated or my hash function should be in a way that it leads to values 0 to M minus 1. So one simple method for this can be that K will be applied with some A as a constant. Then I will take mode of 1. What does mode of 1 mean? I'll explain. Multiply with M and take a ceiling of this. This can be one way where dependency on M gets reduced, and I can get some better distribution still possible, where M will be used to decide. Of course, this range will come this. So what is A? It is a value in between 0 to 1. The purpose of all this is that Ka, even if K is integer, multiplied by some A, it will lead to some real number. And Ka mode 1 will give its fractional part only. So Ka mode means fractional part only taken. The purpose is extract the fractional part. Once fractional part is taken out, of course, it will be in the range of 0 to 0.9999. And if this multiplied by m and then floor taken, obviously it leads to the corresponding scale of, I'll just shift slightly, and it will automatically bring my indexes to be in the range of 0 to m minus 1. So this is the purpose, what we are doing. I'll just quickly go and show once again, discuss all those things in more detail. So when I said Ka is taken like, so let's assume K was, let's say 75. A is, let's say, chosen as, let's take it as 76. A is chosen as, let's say, 0.3333. So Ka will effectively mean 25.3333 and so and so. I'll say take its a fractional part outside, 0.333 taken. So if my m is taken as 1000, m into 0.333 will effectively mean 333, even if it is this. So floor of that will be taken. So 333 becomes the index. So that is the whole purpose of doing all this. We can easily understand that some random behavior or some random distribution will get guaranteed through this process, and random distribution will ensure lesser collisions. But how to calculate effectively mode 1? So Ka mode 1, how to calculate that in programming? How to do this? How mathematically to do? Effectively, it means that out of 25.333, I should be able to minus 25. That will be able to do that. How to do that? I can easily say Ka minus, take the int value of Ka. You can easily get that. So Ka int value of this will give me the corresponding integer. Mathematically, I can say this is equivalent to saying Ka minus floor of this K. So this will become the corresponding fractional part. And I can do that. So this is another method. This will be used to have this. So in this case, choice of m is not that critical and still random distribution is possible. There can be other ways also. So this is how your hash function is chosen. Having said that, let's continue to talk that we talked of a chaining as a solution. But chaining has its own requirements. One, it requires a pointers. Secondly, it requires a dynamic memory. The dynamic memory which is being used correspondingly for the overflows. Whenever there is a collision, we need to allocate one extra node. Allocation of extra node will require extra memory, and this will be for all overflows, and pointers means even any node will be stored via dynamic memory. So my total memory is m slots plus something multiple times more than that, and all that happening. Yeah, can be one way, but there can be second way also. So the other method which we used was called as open addressing. So both methods have its own pros and cons. In open addressing, no pointers will be used, no dynamic memory will be used. All records or all key-based records, keys indirectly mean the full records, to be stored in storage table only. That will mean that this should be large enough. How much large? Obviously, if there are n keys or n records to be stored in m slots, and if I am not allowed to go beyond st, it will imply that m must be greater than equal to n. Only then you will be able to ensure open addressing. That indirectly means alpha will be always less than equal to 1. Hence, I will prefer to apply this method if I am able to ensure the corresponding m value. And I will choose m accordingly. So choose your m to be greater than this. If I am able to do that, then what will happen next? So I'll say, if I am able to continue like this, then I can easily say, in this case, what will be the logic? So if there is no collision, problem is not there. Simply the slot is available, store. But if collision, where to store? So the choice in this case is in ST somewhere, in ST only. And ST only means your index still has to be 0 to m minus 1. So that means I have to find a new index in case of a collision. So new index to be found again in the same range. How to find that? So there are three methods. One method is known as a linear probing. Second method is known as quadratic probing. And third method is called as double hashing. So we will see their pros and cons one by one, but of course, this is best out of all three, and linear probing is worst out of all three. And why? We will understand once we know their working. So let's go one by one. Linear probing. Linear probing simply says that if collision, then you will be storing the value linearly at next address, or I'll say at next linear location, linear slot. Means what? Say I have this hashing table ST. Say you got some key value K1 to be stored. Say H of K1 got this address. You stored here K1's record. No issues as there was no collision. So K1's record stored here. Now you got another key K2, let's say, which also mapped to the same address. Leads to a collision. So the solution is, if next location is free, store here. So my K2 will be, if it is a free, this K2 will come here. K2 plus full record will be stored here. Sometimes later, you get another H of K3. That also, if I assume maps to the same address, next location is also not free. Next is free. So my K3 will get stored here. So linearly, I am probing to find the next location for the storage in case of a collision. This is what called as linear probing. Of course, it will have its own advantages and disadvantages, but this is what method says. Now, if I say this is linear probing, I might reach to the last. In case I reach to the last, some above locations could be free. I will be going further, taking the mode and always revolving into the corresponding place. If I reach back to this location after probing everywhere, overflow will be possible, but it will not happen if I have chosen M correctly. Never it will happen because I have chosen M to be greater than N or greater than equal to M. But if I have chosen M wrongly, of course, overflow may happen. So this is the linear probing. How to implement that? Maybe if I say I want to insert. So I say in linear probing, if I have to implement insert some key value K to be inserted into my storage table given to us, how to do that? I'll say effectively nothing but first of all, I will apply the index to be calculated. I will say index equal to hash function applied over key. If my this location is a free, equal to null or -1 or whatever, then I can easily store and come out. Else, if it is not free, that means it is already full. There is an overflow. Effectively, what I am doing is index to be incremented, and it will mean go to the next location. While location going to the next, I might go to the last mth -1 position. So just to make sure that I keep on circulating within the total space, from here I go back to this upside. So I can just take mod M and I can again prefer to do this. Loop this. How many times should I loop? Till I don't get a space or till overflow happen. effectively, approximately, it will mean either m times, it will be guaranteed. So, or if m times also it is not getting the space, then either overflow will happen or the space will have come. If m times also not, I am not getting the corresponding value, if then overflow will happen if loop exhausted. So that also I can accordingly write. So this becomes effectively the linear problem. Of course, there are advantages and disadvantages, but mathematically, if the same thing is to be implemented, we have a different way of doing this. So mathematically, I say all this linear problem is also defined as a hash function. So I say hash function now I define with iteration wise, initially I equal to 0, and if collision I equal to 1, if again collision I equal to 2. So probe sequence is this one. Let me just shift my this. So my probe sequence will be I being changing from 0 to onwards, and it is nothing but it is h of k0 plus I mod m. So mathematically, it is one and the same thing which I have written, and this was my original hash function. So just telling this because in the book it is explained like this, so you get better clarity by understanding this, but it is effectively equal to your linear probing plus I every time, initially 1, initially 0, if nothing is a collision. If collision, this is a linear probing. And always going in that particular manner. So accordingly, the flowchart or the pseudocode which I have just written correspondingly can be modified, that for insertion into my linear probing, I can easily see can be initially take I0, and then I'm going to have index calculated every time by applying h of ki, and this mathematical function will calculate. If the location is free, I will store there the corresponding record, else I will increment I or index again. So else I will mean I to be incremented. I increment will mean automatically the corresponding hash to be recalculated, and every time doing like this. So more or less same thing, just mathematically written in a different manner. But time complexity of insertion. Worst case, it is going to be order of m. So, of course, not a good solution, but yes, this is the fact. So that's why we say probably we have to think of time complexity of a searching as well as insertion. And if all are not good, obviously, this is not good. So let's go to searching operation. How will we search? Now, search also, I will simply say, first of all, I will apply to get the index. So I can say index will be h of k0. If st index has got some value, is this the key which I am searching? Not sure, because that location could have got synonym of some previous location or some previous collision. So I can't still expect this. Here it's a key value also I have to match with the k, or before that I will say rather if it is null, obviously means nothing is stored. So this means not found. Else, even if the location is full, correspondingly, the key matching has to be done, because it might not be the same key which I am searching. So if I am searching for a different key, I have to check that. If this, obviously found. If not found, where it can be available. Yes, you can smell. If it is not at this location where this is supposed to be available, I can easily say this is probably going to be available at the next linear address. Effectively will mean go to index plus plus. Or in general, I will say, take it as I, and I can have here I plus 1, I equal to, or I'll say I plus plus, and every time my function will be calculating the corresponding next address. So this I can keep on repeating, and I can have a loop to decide. If I apply like this, you can easily see this will also correspondingly calculate, and corresponding worst case time complexity, this case also becoming order of m. So again, not a good choice. Then think of a deletion. Delete. Again, delete also in the similar way. You can do compare, and if found, maybe you will have the corresponding st at that location to become equal to null for future, so that it is deleted, and before that any returning etc. to be done. Worst case, this will also be order of m. So in all three operations, insertion, search, delete, all becoming order of m, in worst case, it's not a good solution. Hence, linear probing not good at all. But beyond not good, it has certain inconsistencies also created. Inconsistency can get created through delete. Can you think why? Through delete, effectively, my search can fail in a wrong way. Why? Can you imagine? Let me explain. I have a storage table. Let's say I got some K1 value coming. It mapped to this address. So my hash applied K1 0. Let me just put this side. And you mapped to this. So K1 record stored here. Later, you got, let's say, some value K4, which mapped to this address. So I have K4 here. Let's assume now came H of K2, which is the same as H of K1. So mapped to this, and then because of overflow, your K2 gets stored here due to linear probing. Because next location was full, so it came next, and so and so. So now this is there. Now assume a request comes to delete K4. This will work perfectly, no issues. K4 is deleted, and this is considered as null or empty. Deletion done. Now, if the request comes for searching K2, what will happen? You started searching at H of K2 0. It is already full, but key is different. Key is K1. So that means go to next hash function, H of K2 1, effectively means next address. Next address effectively means it's empty. And I conclude that it is not found, although this existed. So this is incorrect. And it happened all because the deletion has made an empty space in between, and next time the search will fail. So this is going to be another problem which we have to solve. How to solve? What was the solution? And this problem actually existed when initially databases were using this hashing function, linear probing function. And at that time, in a DBase software, there was a software known as a DBase. DBase initial versions in 1980s were used. And at that time, they had got this issue. So the solution was that they didn't delete. Delete meant not physical delete, mark for deletion only. And mark for deletion so that while searching, etc., you are able to compare the key and this location is not considered as empty, only marked this, and all search and insertion and deletion were supposed to work like this, so that that location is never considered as empty, although this has been deleted. And once there are sufficient markings done, then you have to readjust the corresponding hash table. Sufficient marking, then only you will do the physical deletion after adjusting all hashes and all current data stored. So current keys in ST, they have to be stored appropriately through the corresponding hashing addresses, so that their logic doesn't fail. So all that has to be done at some stage, and physical deletion used to be done later, which was obviously quite time consuming, because this activity will take a lot of time. All those values which are available, they have to be put at their corresponding addresses, etc. So this was the issue with the linear probing. So hence, we said that linear probing is not a good solution at all. Let me just again have saying, okay, I'll start from here only. So I can say linear probing was not the corresponding answer to this situation. So linear probing was avoided and a second method was used. Before that, linear probing has another problem of a clustering being created. It started giving a clustering issue, which is called as a primary clustering problem. What is that? I will explain. So what it said was, in the storage table, after some time, clusters will get developed. Why? What is the probability of storing any value at this location? Let's say index 0 or any index 1. I say in general probability, I can say by default is going to be 1 by m. There are total m values to be stored, let's say, or n values. So probability could be 1 by n or 1 by m, because each location is equally likely to get some data. So I say uniform hashing will ensure each probability to be 1 by m, any location. But let's assume location 5 is full. Location 6 is also full. Location 7 is also full. Location 8 is also full. All are full. Now, what is the probability of filling 9th location? This probability, ideally, it should be 1 by m, but it is not anymore 1 by n. Why? If some value was supposed to come to address 5, that will also come here. Some value was supposed to come to 6, that will also come here. Some value was supposed to come to 7, that will also come here. Some key value was supposed to come to 8, that will also come here. And any value which was supposed to come to 9, that will also come here. So this probability effectively becomes 4 plus 1 by m. And just above, there are 4 full locations. 4 full slots exist. That increases the probability. So probability of next slots increases much more. So consecutive slots filling or slots will be filled more frequently after some time if I could get initially few consecutive filled. This will happen more, and this probability is more probable, and this problem is called as a primary clustering. So linear probing has lots of problems. The problem came because I was storing the data at immediate next position. So consecutive locations were likely to get filled and clustering, primary clustering used to happen. Hence came a better solution. So then came the second solution, which was called as quadratic problem. Quadratic probing said, don't store the synonym or collision based data at immediately next place. Quadratic probing. So what it suggested was that if you have some storage table, you have stored some data, let's say here, you have got this location correspondingly for h of k1. If h of k2 also comes here, don't store at next place. Give some offset and try to store somewhere here, so that primary clustering doesn't happen. So give some offset. And offset also, they decided not linear offset, but a quadratic offset. How did they decide? They said, go for hki to be nothing but first function is obviously original function. If this doesn't work, then give it an offset of quadratic nature. Of course, mod m to be applied, and this becoming the offset. So C1i plus C2i square. So if I is 0, obviously nothing offset will come, but later this whole becomes an offset, and this offset is not a linearly growing, so it will be able to avoid primary clustering. And rest of the process remaining similar. So you have to decide your insertion, you have to decide your searching, and you have to accordingly plan deletion for quadratic probing. So accordingly, those pseudo codes or those solutions you can easily decide, and primary clustering gets avoided. But this has got another problem, lesser critical problem, lesser problematic issue of clustering comes, which is called as secondary clustering. What is that? I'll explain. So it's not as bad as primary clustering, but what it says, synonyms will always have same probe sequence. That is the only problem. Not, of course, as problematic as others, but still this is there. Means what? Let's say I have some key value k1. Its first index comes as, let's say, address 5. If there is a collision, then next address comes as, let's say, 23. Or maybe, let's say, 13. C1 and C2 are some constants, so I chose a C1, C2 in a way that I reached to this. Next address, let's generate it as 27. Next generated as, let's say, 55. Next generated as, let's say, 2. And like this. Of course, I will ensure that next time 2 again doesn't lead to a cycle of 5 itself. So I'll never reach to the same cycle again and again, but some days. But a synonym comes of K1, let's say K2, that will also have the same sequence 5, followed by 13, followed by 27, followed by 52, followed by 2, and so and so. And why? Because this offset was directly dependent on C1i plus C2i square. C2 and C1 are chosen once as some constants. This will remain constant. So if h of K0 was the same, then all subsequent probes will also remain the same. So that is probably creating a problem for synonyms. So secondary clustering will happen for synonyms only, and synonyms will have a more possibility of collision if there are already certain synonyms existing. So if there are already few synonyms already existing, then next synonym will have much poor time complexity, and that leads to some deterioration of the performance. How to solve that? So then came the best solution, which is known as double hashing. So double hashing is the ideal solution, which is best or better than others because it avoids even secondary clustering also in a way, and this can be used. And in fact, many processes of the computer engineering, including cryptography or networking and hashing actually applied, they use this particular technique. So what they say is your offset will be also a hash function dependent. Another hash function will be taken, and that hash function will generate a different values, maybe for another different set of synonyms. What does that mean? It said that h of ki will be equal to nothing but h1 of k plus I into h2 of k. Of course, mode taken of this. So mode will be obviously taken, but this was first time. I equal to 0 means h1k used only. If collision, then correspondingly h2 comes into picture, and my h2 function will also be used, and h2 can be designed in a way so that for the same synonyms, next time h2 gives a different value compared to the same value again. If I can ensure that, then I can design h2 smartly, and h1 and h2 being different kind of mathematical calculation, and synonyms can also get different address. So this will solve that problem also, and accordingly, I will be able to perform better. So I will just wind up my discussions here. The analysis of the open addressing also to be covered, and like we have yesterday talked of synonym chaining analysis for searching, etc., time complexity, etc., that is given in the book as theorem 11.6. You should read it. The aim is simple, that we want always the time complexity not to be high, especially for the searching. So search time complexity, I should know, and whether I'm able to do better or not, that is always my aim. Of course, insertion and deletion are also important, but search is the most frequent operation. So we would like to see in successful or unsuccessful cases how much time complexity via open addressing will happen on average. So this also calculates some probability and expected values, and accordingly some expected value of E of X to be calculated, and all that calculations given in the book. You should read that and practice that out. It's easy, but you should do that. So with this, I think I'll stop here, and now let's